Greetings to the respected faculty. I'm Lasya Mandapati from CSC AI&ML D section, and today I'll be presenting on the topic Smart ATM Secure as a part of the course Database Management Systems for the Complex Engineering project. This project focuses on designing a secure ATM system using DBMS concepts. Now, ATMs are something we use almost every day, but we rarely think about what happens behind the scenes. Every transaction we perform, whether it's withdrawing cash or checking balance, is actually handled by a database system. So, in this presentation, I will explain how a secure and reliable ATM system can be designed using database schema design, security constraints, transaction management, and encryption. Now, let me briefly walk you through the structure of this presentation. We begin with the abstract, followed by an instruction as to what a smart ATM is. Then we move into the need for security in ATMs and the problem statement. After that, we focus on the core DBMS part, including database design, tables and relationships, and security constraints. We also discuss authentication, transaction processing, encryption, and finally we conclude with results and insights. A smart ATM is not just a machine, it is a combination of software, hardware, and a database backend. The database plays a crucial role because it stores customer information, account balances, and transactional records. In this project, the focus is on applying DBMS concepts such as normalization, constraints, authentication, and transaction management. Additionally, security mechanisms like encryption, access control, audit logging, and more are used to prevent fraud, protect sensitive data, and ensure system reliability. A smart ATM is an advanced version of traditional ATMs. Unlike basic ATMs, it supports multiple services such as cash withdrawal, deposits, balance inquiry, and cardless transactions. It also uses advanced technologies like cameras, sensors, network connectivity, and more to monitor activity and detect suspicious behavior. Modern smart ATMs also include biometric authentication, OTP based verification, and mobile integration. This makes them more secure and user friendly. ATMs are highly vulnerable to attacks. Some common threats include card skimming, shoulder surfing, malware attacks, and physical tampering. Since ATMs deal with financial data, any security breach can result in financial loss, data theft, or loss of trust. The database stores very sensitive data like account details, transaction history, and authentication credentials. So it becomes extremely important to prevent this data from leaking and prevent unauthorized access to this data as well. So the main objective or problem statement is to build a secure ATM system that correctly authenticates users such that it protects data and prevents unauthorized access to any other users. This in turn minimizes the card based fraud, PIN theft, and insider attacks by enforcing strong DBMS level constraints. The main problem addressed in this project is how do we design an ATM system that is secure, reliable, and resistant to fraud? To do so, the system must correctly authenticate users and process transactions safely, as well as protect stored data. It should also prevent insider attacks, enforce strict access logs, and maintain audit control. Another critical requirement is ensuring acid properties so that even if a system failure occurs, the database remains consistent. Now, let us look at how these tables are connected. The customer table stores basic details like customer ID and customer's contact info. The account table is linked to the customer using a foreign key. Each account can have multiple cards and multiple transactions. This creates relationships like one to many between customer and account and one to many between account and transaction. These relationships ensure data integrity and proper linkage between the records. Database management systems provide several built in mechanisms to ensure security. First, we have primary keys and foreign keys. These maintain data integrity. Then, we have check constraints and triggers. These enforce rules like minimum balance and withdrawal limits. By implementing these at the database level, we ensure that rules cannot be bypassed, even if the application layer is ever compromised. Authentication ensures that only valid users can access the system. This can include PIN verification, OTP verification, and biometric verification. Access control ensures that users only access what they are allowed to. For example, a customer can only access their account and not any other customers. And bank staff have limited permissions as well. This is implemented using role-based access control or RBAC. This minimizes the risk of unauthorized access and insider threats. Every ATM is treated as a database transaction. These transactions must follow ACID properties, ACID, where A stands for atomicity. All operations succeed or no operations succeed. Next, C for consistency, where the database remains valid. I for isolations. This means that transactions do not interfere. And finally, D is for durability. This means that changes are permanent. For example, during a withdrawal, balance must be updated, transactions must be recorded. If any step fails, everything must be rolled back. This ensures reliability and prevents data corruption. Encryption and audit logs. PIN card numbers and sensitive fields should be stored in encrypted or hash forms to prevent exposures even in the database so that if in any case there is unauthorized access or insider leaks in the database, these hash forms or encrypted data is not leaked. Hence, the database must maintain an audit table that logs successful and failed login attempts. And role-based access control or RBAC restrictions should be placed on who can view and modify sensitive tables. Sensitive data must always be protected. Pins and card details are hashed and encrypted, like we discussed before. Even if the database is compromised, this prevents attackers from reading actual data. And the audit logs record login attempts and transactions as well as machine activities. So, in case there is any fraud or suspicious behavior, these logs are useful for detecting and analyzing them. Hence, the system demonstrates that a well-defined and well-designed database can improve security, ensure data integrity, and support efficient operations. By applying constraints, access control, and encryption, we reduce the risk of attacks significantly. However, there are challenges such as performance overhead, key management, etc. However, these can be handled carefully in real world systems as well. Thank you for your time and attention. I hope this presentation can give you a clear understanding of how DBMS concepts are applied in ATM systems.